In this video, we are going to be talking about vectors. So what is a vector? A vector is something that has a magnitude and a direction, and it can be used to represent a lot of things. So it has a magnitude, which you can think about as how much of whatever you're representing, and the direction is just the direction. So for example, let's say if I got a car and I'm driving 600 miles per hour, and I'm saying I'm doing 600 miles per hour to the right. So notice how the 600 miles per hour part, that's kind of like my magnitude, right? It's how much, it's kind of like my speed in this case, right? And to the right, that indicates the direction of where I'm going. So you can see how this, in this case, would be referring to velocity, and velocity would be a vector. Okay? So when I'm saying like 600 miles per hour to the right, or 300 miles per hour to the left, or up or down, whatever, that's going to be referring to velocity. So velocity, you can kind of think about it as just speed, but it has a direction. Okay? And this is different from a scalar quantity. So scalar quantities, I'm just going to write this to the side. So scalar quantities, they only have a magnitude. So it's not like a vector quantity where there's a magnitude and a direction. So for example, if I say it's 400 degrees Celsius outside today, okay, that's just a magnitude. There's no direction with that. If I say this guy weighs 50 kilograms, okay, that's just a magnitude. Another thing, let's say if I'm going 50 miles per hour, notice how I don't have a specific direction that's mentioned, right? I could be going 50 miles per hour up, down, left, right, whatever, right? And so because there's not a specific direction that's mentioned, speed is an example of a scalar quantity, okay? So while velocity is a vector, velocity is a vector quantity because it has a magnitude and direction. Speed is a scalar quantity because it only has magnitude. So that's the first important point that y'all got to know. Now we're eventually going to build up to calculus 3. And so we want to actually represent vectors in kind of like a math way. So how can we think about vectors in like a math sort of way? Well, you can think about the coordinate plane, right? There's an x-axis, which is here. There's a y-axis. And a vector can just be represented by an arrow. And in many cases, it's going to be an arrow starting from the origin and pointing towards somewhere in some direction. And so this would be an example of a vector. This would be an example of a vector. It doesn't have to start at the origin, but in many cases, you will be dealing with vectors that do start at the origin. But I'm just going to draw out a couple more arrows to give you guys the experience. But yeah, all these are examples of vectors because they have a magnitude, which is represented by the length of the vector, and they have the direction, which is, of course, where the arrow is pointing. Now, if I have a vector that looks like this, and let's say if I copy and paste this vector, let's say I take this one, I copy, I paste it, but instead of starting from the origin, let's say it started here. Would these two things be considered the same vector? What do you think? Well, these two vectors would actually be considered the same vector, okay? So it turns out that your starting and kind of ending position, it doesn't really matter as long as, you're pointing in the same direction and you have the same magnitude, you're still going to be the same vector. Now, you refer to the end of this vector, you refer to it as the tail. While you can think about it as the front of this vector where the arrow is, you can think about it as the tip. Okay? And we'll be utilizing this vocabulary when we're discussing vector addition, which we will promptly do right now. So how do you add two vectors together in mathematics? How do we do this? Well, think about it like this, right? Let's say if you originally go 2 units up, okay? So let's say this is the first vector, which represents you going 2 units up. After you go 2 units up, you decide to go 2 units to the right. So it makes sense that when you're representing vector addition, right, when I first go 2 units up and then 2 units to the right, you can kind of think about it as like this vector right here, the head or the tip of the first vector goes on the tail of the second vector. So, right, I first start walking, let's just say, and then I end off here. This is where the first vector carries me. I'm on the tip of the first vector. And now the second vector, the tail of the second vector starts carrying me through to my final destination. So this is something called the tip to tail method for adding vectors, okay? All you do is, and this works with weird vectors that are in crazy, it can be at an angle, whatever. But if you have, let's say, this first vector, and you want to add it with another vector, you literally just put the tip of the first vector on the tail of the second vector. And you can chain this as well. So this can work for many, many vector additions. So I'm just gonna give more diagrams as a visual aid for y'all. But you can see that, right? All you have to do is just take the next vector, just place it directly after where you left off, right? And then you just continue from there. So you can think about each vector as like a journey somewhere, and you just end off where that vector carries you. And let's say if I have this first point, let me call it A. And let's say I end off in the second point. Let me call that B. Let's say that A has the coordinates 2, 2. And let's say that B has the coordinates 7, 3. How can I find the vector that points from A to B? Well, you can see that, well, this first initial A right over here, since it starts at 2, 2, right? You can think about from the X direction, this thing starts at 2 and it ends at 7, right? The X value starts from 2 and ends at 7. Therefore, in the X direction, we have traveled 5 units, right? So in the X direction, we have traveled 5 units. And since we go from a height of 2 to a height of 3, well, then we have traveled 1 unit up. So take a look at that. You can represent the vector AB, right? The vector that kind of connects these 2 points as basically just having the values of, well, 5 in the X direction and 1 unit up. And there's your answer. Now, if you want a formula for this, notice how all you have to do is just subtract the second vector values from the first vector values. So notice how 7 minus 2 gives me 5, and 3 minus 2 gives me 1. So if I have 2 vectors, let's say I have v1, if I have 2 points, x, y, let's just say x1, y1, and let's say we have x2, y2. And let's say I want to find the vector that connects these points. Well, then it's just going to be y2 minus y1 for the y value, and then x2 minus x1 for the x value, and that's going to be your vector. Okay, that was a horrible box and horrible spacing, but you get the idea. So recall the value, or recall the vocab word absolute value. What does absolute value mean to you? Could just mean another like math term that you kind of hate, but what is absolute value? So let's say if I have the number 3. The absolute value of 3 tells me how far away is 3 from the origin, or 0. And you can see that it's a distance of 3. And same thing with negative 3, right? The distance from negative 3 to the origin is going to be 3. So what does it mean to take the absolute value of a vector, right? Since we established that absolute value is the distance from the origin, well, you can imagine that this can also apply for vectors, right? Imagine if I have a vector that's centered at the origin, and let's say it branches out to the coordinate 3, 4. Well, then the absolute value of this vector, let's call this vector v. So the absolute value of the vector v, I'm just going to write it without the arrow because I'm too lazy. This is just going to be essentially the vector's length, right? It's the distance that it has from the origin, which is just like the length of the vector. And so to calculate the length, well, vectors, you can think about them as having a x component, right? Since vectors are represented by arrows on the coordinate plane, they were represented by some sort of x direction, 3 units in the x direction, and some direction in the y direction. And so this just becomes a Pythagorean theorem problem, and you might recognize this as a 3, 4, 5 right triangle. And so the absolute value of v, in this case, vector v, would be 5 units. Now, I really want to solidify your understanding and make sure that you're not just watching this video for like the funsies, Like, you actually gotta understand this if you're trying to get good at it. So we're gonna do some practice problems, and I highly, highly encourage you to try out these practice problems before I do it. That's like the best way to learn these concepts, okay? Because when you're building up more advanced concepts, you're gonna need these foundations. So vector magnitude, find the magnitude of this vector right over here. And sometimes you might see the vectors represented by these little HTML, little equal or greater than less than signs. So how would you do this? Well, you can visualize this, right? So these problems are luckily not to the point where you can't actually visualize them and you just have to plug it into the formula. Like, look, you're going 3 units in this direction, in the x direction, -4 units down. And so to find out the missing value, just use Pythagorean theorem. And once again, this is just going to be another 3, 4, 5 right triangle, right? So just going to get 5. And so it's pretty nice that even though that vector has a completely different orientation than the vector that we saw before, it's still going to have the same magnitude, which is pretty nice. 2, the 3D magnitude. So you might recall that x squared, right, plus y squared, is equal to the magnitude of the vector squared. So I'm just going to say the magnitude of v squared. Right, so what you saw in the last problem we did, was that we said that the magnitude of the vector is equal to the square root of the x value squared plus the y value squared. Well, if we're dealing with 3 dimensions, right, well then you're just going to have to add a z squared to the end. So when you're in 3 dimensions, not only do you have an x and a y value, but you also have a z value. So that's actually where it gets a little more complicated. But in terms of like a lot of formulas that you know in 2D, that can actually work out really nicely in 3 dimensions. And this is one example of it. This is the magnitude formula. And so, how would you do this one? Well, you just have to use the magnitude formula down here. And so 2 squared plus, what is it? -1 squared is 1, and 2 squared is 4, right? So this is just going to be equal to 9. And then so if I take the square root of 9, I'm just going to get 3. So the magnitude of this vector is 3. Vector addition. So when we want to add these two vectors together, right? Remember, tip to tail. So when I'm at 4, -2, well, that's going to be around right here, right? 4, -2. And I'm going to add that with -1, 5. So you can imagine that I'm going back in the x direction by 1 unit, but I'm going up by 5 units. So I'm going to, let's just say somewhere here. So that means that the resultant vector is going to be from the origin to this vector right over here, right? You travel, think about this as like a travel trip, right? You travel down here, you travel all the way back up here. So your net displacement from the origin is going to be represented by the brown vector. And the way you do this, well, once again, you just add up the values, right? So for vector addition, 4 plus -1 gives you 3, and then -2 plus 5 gives you 3 as well. So that makes sense because, well, if we go forward 4 units and back 1 unit, we're going to be at x value 3. And if we go down 2 units, but then we go up 5 more units, then we're also going to be at 3 for the y value. So you can kind of treat these vectors as little like paths that you take. And the net path that you take is going to be the sum of the tiny paths. So vector subtraction, it's the same idea, except you just subtract. So 7 minus 2 is going to be 5. And, well, in this case, this is going to be in 3 dimensions, but still going to work out. 3 minus -4, it's going to be 7. And -1 minus 5, that's going to be -6. So that's going to be your vector. Okay. Multiplication. So this is actually really nice. So vectors, right? They can be scaled. So let's say if this is the original vector, v. If I multiply v by 2, well then this arrow is just going to get longer, right? You can think about it as if I just took this vector right over here and just stacked it on top of each other. Because recall that if you have 2 times v, that's just the same thing as v plus v. And guess what? You can do the tip to tail method, and you just end up with kind of the same vector, but it's just 2 times longer. This is actually really, really nice. And so what you'll find out is that this number in front of the vector is called something called a scalar, because it just scales whatever vector that you're doing it on. Okay. So when we were talking about scalar quantities beforehand, well, we were talking about something that has only magnitude, no direction. Well, guess what? The number 2, it only has magnitude, no direction. In fact, any constant that I put up here, if I put, let's say, 3 times this vector, 4, any constant times this vector, that is going to be a scalar quantity. Okay? And what you do mathematically is you just multiply all these components by -3, right? Because that's the factor you're scaling everything by. You scale in the x direction, you scale in the y direction, you scale in the z direction as well in this case. So you're just going to get -6, comma 3, comma -12. That is going to be your answer. All right, now we're going to have more conceptual questions. So we're going to determine whether each quantity is a vector or a scalar quantity. Temperature, 200 degrees Celsius, that's just going to be a scalar quantity. Velocity, we said that was a vector quantity. Speed, that's also a vector quantity, or sorry, a scalar quantity, sorry. Velocity is basically speed with direction. Okay. Force. Now, if I have a box and I'm applying a force on it, you might remember this from physics, but force, if I apply a force to something, it's going to have a direction, right? Where am I pushing the box? Am I pushing the box from underneath? Am I pushing the box from left, right, up, down? Where am I pushing it? And so the direction of the force, well, now that, that got to come in play, right? So this is going to be a vector quantity, right? Distance, well, if I just said that I walked 30 meters, well, I could be walking 30 meters up, sideways, upside down, I don't even know. So that is just going to be a scalar quantity because that only gives me the magnitude. But if I say something like 30 meters to the right, which is displacement, well, then this is just going to be a vector quantity. So you can see how displacement is basically just distance, but vectorized. It has a direction as well. True or false? 2 vectors are equal only if they start at the same point. No, we saw how 2 vectors starting at different points can be the same vector. So, no, that is going to be false. Can 2 vectors have the same magnitude, different directions? We already saw that, right? Remember when we had the vector that points up to 3, 4? Well, that's going to have the same magnitude as a vector that's pointing down to 3, -4. Because when you're dealing with the Pythagorean theorem, you're going to be squaring everything. So all the negatives are going to just turn into positives. So same magnitude, a different direction. You can also connect this to absolute value, right? In the number line, right? You can see that the absolute value of 3 is the same as the absolute value of -3, right? There's the same distance from 0. And you can kind of see this, I guess, symmetry applied in, 2D. Okay. So let's say that we have a vector that's -3, 4. So -3, 4. It's up here. So we want to describe the horizontal movement, the vertical movement, and the quadrant. Well, this points into quadrant 2. We're going 3 units to the left and 4 units up. So there we go. A plane travels 5 units east and then 12 units north. What is the total displacement? And we want to find the magnitude. So let's see. So east, so never eat sour watermelons. So we are going to be going 5 units east and then 12 units north. Same thing as going up. Therefore, our resulting vector is going to be the one that points from the origin to the final spot, right? Right? You can think about these vectors, once again, as individual trips. Go here, and then go here. So the resultant vector is just going to point from the origin to the second vector here. It's just the net displacement. And this is, once again, the Pythagorean theorem that you might recognize, from the past. So the magnitude of this is just 13. 13 units. Unknown component. A vector has a magnitude of 13 and a component of x comma 5. And we want to find all possible values of x. So how do we do this? Well, we can set up this problem here, right? So we know that the y value, this 5 right over here, tells me that this vector is going to be somewhere up here. So I can have a vector that's like this, where the length of it is 13, right? The length of it is 13, and we know that's 5 units high, and we want to find out the specific x values. So we know that, let's just say this is x right over here. We know that x squared plus 5 squared is equal to 13 squared from Pythagorean theorem. X squared is equal to 144. And if we square root this, we get that x is equal to plus or minus 12. And it makes sense that, just looking at this diagram, 12 units here and 12 units back, makes sense that we get the same, magnitude for those ones. And finally, last but not least, opposite vectors. Find a vector with the same magnitude as 6, 8, or negative 8, but pointing in the opposite direction. So if I'm going 6 units, 8 units down, so that's negative 6, 8. And it's saying pointing in the opposite direction, so I guess we can go this way. So this is going to be negative 6, 8. Okay, so that's just going to be the vector that points in the opposite direction, right? You have 6, negative 8. And then if it points in the opposite direction, it's kind of like you rotate it by 180 degrees, right? So you're just going to negate everything. So it's going to be negative 6, and then negative 8 becomes just positive 8. Vector, let's say if this is at 3, 4. Now you could just represent the vector like this. But some mathematicians came up with this idea. So imagine if you had unit vectors. Unit vectors just means that they're just these vectors that have a length of 1. And in this case, right, the unit vector in the x direction would just be a vector that's length of 1 and going 1 unit in the x direction. And I'm just going to call this unit vector I. While the unit vector that's going 1 unit up, I'm just going to call that unit vector j. Now you can imagine that if I stack 3 i's, or you can imagine that I have 3 i's, and then I add this with 4 j's, right? So I add this with 1, 2, 3, 4 j's, right? Using, the tip to tail method and all that. Well then, I get the same resultant vector. And so this ij notation is very, very common when you're representing vectors. So if you want to just convert from regular vector notation to ij notation, you just do your x value times I plus, because remember, this is kind of like vector addition where you're stacking it, and then 4 times j. And if you're dealing with 3 dimensions, let's say this is x direction, y direction, z direction. Z represents the height. Let's say if I have a vector that's, or let's say, I don't know, here. I'm choosing a random one. Let's say this is, I'm just making up coordinates. Let's say this is at 1 for the x value, 3 for the y value, and 2 units for the z value. Well, if you want to represent this in ij notation, well, this would just be 1i, or I just write I, plus 3j. And then the letter that we use for the unit vector in the k direction, or sorry, the z direction is, I kind of spoiled it, but it's k. So ijk, that's really easy to remember because they're all right next to each other. So yeah, that is the way you represent the vector using ijk notation, okay? And if you want to make a vector into unit length, so let's say if I have a vector here, 3, 4, is there any way that I'm able to shrink this vector so that it's still pointing in the same direction, but now it just has a magnitude or a length from the origin, distance from origin of 1? So that's something called normalizing a vector. You're going to make it a normal length. How do we do this? Well, all you have to do to normalize a vector is, well, you have to find out the magnitude of it. So in this case, once again, we know that this is just a 3, 4, 5 right triangle. And so the magnitude of this vector, the magnitude of v, is going to be equal to 5. And what you do is you take each of these components and you divide it by 5. So the normalized vector would just be 3/5, comma 4/5. And that's your answer. That is the normalized vector. Okay? And if you actually use the Pythagorean theorem to solve for the magnitude, you'll actually find out that, well, you have 3/5 squared, which is just 9/25, plus 4/5 squared, which is just 16/25. That adds up to be 1, and then the square root of 1 is just 1. So that's how you would normalize a vector. All you have to do is just find the magnitude of it and divide each of the components by it. And this applies for 3 dimensions as well.